Hello everyone and welcome to today's webinar on Fortran verification using the NAG compiler. Thanks for everyone for attending. During the webinar, I encourage you to ask questions, and you should have a panel for questions. You can ask them during the webinar or at the question and answer session at the end, and the slides and the recording will also be made available at the end. Today's agenda is shown here, so I'll talk about why should we still use Fortran, followed by code verification and portability and why that's important and how the NAG compiler can help you, followed by the compilation checks that the NAG compiler can do and the additional runtime checks and the unified precision feature. The compiler also comes with additional tools to help you modernize legacy Fortran 77 codes, and I'll also present some real-world bugs caught by the compiler, and I'll recommend a code verification workflow that uses the compiler, and there'll be approximately 10 minutes for questions and answers. So why should we still use Fortran? Fortran's been around for some time now, and this table shows the percentage of time of applications run on the Archer supercomputer based in Edinburgh. So you can see for Fortran, just over 73% of CPU cycles is running code developed in Fortran, and 80% of jobs running code applications that are developed in Fortran. And Fortran usage statistics for the top 500 supercomputers is around 70%. Fortran also exists in hybrid codes such as Python and Fortran, C++ and Fortran, where the computation-intensive kernels are implemented in Fortran and everything else is implemented in Python. So my conclusion is that Fortran is really the dominant programming language of computational science and engineering. It has been designed specifically for numerical computing and is really the language of choice for high-performance computing. The language is also backwards compatible to older standards such as Fortran 77, and it's really the only compiled programming language to provide parallel fault tolerance, which is in the 2018 standard, which is yet to be published. The Fortran Standards Committee, known as WG5 for short, really work actively with the HPC community to design new standards. So it's a language that has evolved over the years. It's a very modern language. I'll now talk about code verification and why it's important. Code verification is to ensure that the code conforms to the demands of the language specification. You might be aware that a lot of computational codes are becoming very complex, making verification more complicated. Examples of such codes are large weather simulation codes which couple multiple packages. And as we're all aware, bugs in codes can obviously have catastrophic consequences and result in loss of prestige and revenue. You could even maybe get sued if you have a bug in your code. With the advent of open science, codes can easily be verified because the source code is put on the web. However, before you release your code should have some level of verification before made available for other people to use. And verification can easily be automated using static tools as well as the NAG compiler, and that could be included in a continuous integration framework. As we all know, debugging is difficult and can be very time-consuming, so it's really important to find bugs as quickly as possible. And there are quite a few tools out there to help you debug. So the idea is to start with the easier to use tools such as the NAG compiler, and then you can progress to more complex tools such as the GNU debugger. I'll talk about code portability. The compiler is obviously the most widely used tool. Everyone needs one to develop in Fortran. And there are a number of compilers available for Fortran. So sometimes when you upgrade compilers, they can stop compiling existing codes, whereas previous versions of compilers did work. And this can occur when developers rely on a compiler feature which was deprecated by a compiler vendor. For example, if it went out of business, or developers change compilers. Or new version of a compiler catches a non-conformance that prior versions of the compiler did not. Or additionally, a change in a default setting or an assumption by a previous version of a compiler was later abandoned. Subsequently, porting codes to different compilers or new versions of compilers can really be difficult, particularly for large codes, or if you've spent a lot of time using a specific feature. So what's the solution for portability? One of the solutions is to really stick to the Fortran language standard, as this is something compilers try to adhere to, and they do a reasonably good job. And this is really your best guarantee that your code will continue to be useful in the future. The NAG compiler is a strict to standards adhering compiler, which will help you increase the portability of your codes across different compilers. And in the exascale era, code portability is going to be very important. Many of the Fortran compiler vendors are on the standards committee, including NAG. Compiler vendors either focus on performance or error checking, however, not both. The NAG compiler focuses mainly on error checking, but taking care not to impact performance unduly. So the take-home message is that not all compilers are created equal. Some have strengths and weaknesses, and some are stronger than others in some aspects. I'll now talk about the NAG compiler. I believe that NAG compiler is an indispensable tool for Fortran code development. The compiler produces comprehensive diagnostic messages and detects more anomalies than other compilers such as GNU Fortran. It will statically detect errors during compilation, and it also includes a range of runtime checks that produce a useful error message telling you where the error occurred and why, and I'll talk about that later. It also has additional tools that will help you restructure more legacy codes into modern codes. The major release of the NAG compiler is around every 18 months, and bug fix releases are around every 2 months, depending on how often customers create bug reports. So NAG compiler does a number of compilation checks, and they fall into different categories. The first category is informational message, which highlights an aspect of the code that the developer might be interested in. Example of that is an expression in a logical if is a constant. The next category is warning, where the source appears to have an error and worth investigating. An example of that is do loop having a 0 iteration count, or a local variable is initialized but not used. Then there's a questionable aspect of the code. An example of that is using the complex intrinsic function with double precision arguments with no kind argument. In this case, it will return a single precision result. Or a do loop variable is equivalent or is in a module. The next category is an extension where non-standard conforming code has been detected. An example of that is using RealStar 8, which is not part of the standard but was widely supported by all the compilers. The next category is obsoleted feature that's been found in the code, and a deleted feature has been found in the code. For all the categories that I've mentioned, compilation will continue. And also, if the compiler encounters any extensions, obsoleted or deleted features, then they are really good candidates for modernization in your code. And the last category is when an error occurs where the source code does not conform to the standard or does not make sense. In addition to the runtime checks, so the compilation checks, the NAG compiler also has runtime checks, and I'll now list them here. So the first is building a code with the -c present flag as shown here. So line 2, as you can see, I'm calling subroutine foo with only one argument. Subroutine is at line 11. The dummy argument B is optional. However, on line 14, I'm using that argument, but it's obviously not present. When I execute this code, it prints a helpful error message, not just a segmentation fault. It says runtime error, line 14, reference to optional argument B, which is not present. So it tells you where the error occurred and why. The next check is the dangling pointer check, which is invoked with a -c dangling flag. Line 1, I have an allocatable target. Line 2, I have a one pointer, which is a one-dimensional array. I'm allocating vec on line 8, and line 9, the pointer is pointing to vec. However, on line 10, I'm deallocating vec, which means vec p is dangling. So the contents of it is just some junk. So if I execute the code, it says runtime error, line 12, reference to dangling pointer vec p, target was deallocated at line 10, and the code then terminates. It is much better to terminate, obviously, rather than rely on incorrect results. So here it's telling me where the that dangling pointer was used, line 12, and where the target was deallocated, which is at line 10. So this is much more useful. And I would also like to mention that the NAG compiler is the only Fortran compiler that can check for dangling pointers. The next check is for checking for undefined variable usage. So line 5, declaring an array of 1 to 11. On line 6, I'm only assigning the first 10 elements, whereas on line 7, I'm printing all 11. Obviously, the 11th argument is undefined. The output when running this code, as you can see, it says runtime error, line 7, reference to an undefined variable array. And it also tells you in which file the error occurred, if you have loads of files. The next check is checking for procedure argument detection. So to invoke this check, I pass the -C equals calls flag. In line 4, I'm declaring a constant. I'm passing that constant to subtest on line 5. And in line 11 is where the subroutine is, integer, and it takes in a dummy argument integer x, which is intent in out by default. However, as you can see on line 13, I'm assigning the value 10, which I can't obviously do because the dummy argument, the actual argument is a parameter on line 4. So executing this code tells me where the error occurred. Line 13, dummy argument x is associated with an expression cannot assign. The next check is the integer overflow. The NAG compiler does a runtime check, not a compilation check, to detect any integer overflow. The last time I checked, this was the NAG compiler was the only compiler that can do this. So line 4, I'm declaring 3 integers. Line 6 and 7, I'm doing a runtime calculation. And the output of this is shown below. It's saying overflow error. Line 7 of the integer in 32 is, so it's telling you the kind. So it's a 32-bit integer, and it's saying overflow for this expression, and the program then terminates. So it's a very useful feature to have if you're moving from 32-bit integers to 64-bit integers. The next check checks for 0 do loop step, and that's invoked with a -C equals do compilation flag. Line 4, I'm calling a subroutine do loop, passing 1, 10, and 0. Line 7, as you can see, that corresponds to the start, end, and step. Line 10 has a do loop which starts at start, ends at end, and it steps through the step variable. That is obviously a 0. Normally, this would result in a floating point exception, but executing it with the NAG compiler, it tells me where it occurred, line 10, and it says do step value is 0. Again, you can see it's much more useful than a segmentation fault. Next check is for pointer reference checking. Line 2, I'm declaring a pointer, P. Line 3, an integer array. Line 10, I'm checking to see if it's size 11, which is not the case. So which means it will go to line 13. So P is associated with null, so it's a null pointer. Line 15, I'm printing P, which will be null. So executing this code will print this output, which is saying runtime error line 15 in reference to a disassociated pointer P. Program terminated by a fatal error. The next check in the NAG compiler is checking for kinds. So line 22 is a swap subroutine. So the dummy arguments are real, and line 23 shows that they're double precision, real 64. And I'm declaring a temporary local variable on line 24. However, here, as you can see, I say real kind equals int32. Int32 is for integers, not for real. And although some compilers might implement real 64 and int32 the same way, however, this code is obviously wrong. And compiling this code will print the compilation error at the bottom. It will say where the error occurred, line 24, kind value does not specify a valid representation. The next feature of the NAG compiler is the unified precision feature. And this is to help you detect mixed precision bugs. So mixed precision bugs can be very difficult to debug and cause numerical errors, such as solution not converging or it blows up. And examples of mixed precision bugs is shown here. Line 1, I'm declaring a double precision. However, I'm assigning alpha to 1.1. Line 3, I'm saying beta equals alpha squared. So the left-hand side is single precision, right-hand side is double precision. Line 4 is left-hand side is double precision, right-hand side is single precision. So line 3 will be detected by the GNU Fortran compiler. However, line 4 is not detected by the GNU Fortran compiler. So line 1 should be 1.1 underscore real 64. Line 3, you could get an overflow, which is easy to detect. So you'll get some strange values because the value has to wrap round. And the error in line 4 will always be single precision, but it will be very difficult to detect. So this is where you can use the unifying precision feature. To use this feature, you invoke the NAG compiler with the flag shown here, equals NAG4 equals unified precision, minus pp name equals dp, which is the kind value, and minus pp module equals type.mod. So this is where dp comes from. So and that's defined in types underscore mod.f90. So applying the NAG4 command shown here produces the output at the bottom. So line 1, it inserts use kinds underscore mod only dp. So line 3, as you can see, it's transformed the old double precision into real kind equals dp, alpha equals 1.1 underscore dp. And line 4, you can see it's declared that as double precision. So there's no mixing of precisions in line 5 and 6. If I continue to execute the previous code that had the mixed precision bug, this is the error that you'll get. So line 1, so if I print the value of alpha equals 1.1 and alpha equals 1.1 underscore real 64, the output is shown on line 1. So on the left-hand side, you can see it's 1.000, but some junk at the end. And the output of alpha equals 1.1 underscore real 64 is shown on the right-hand side. So as you can see, it's much more accurate. And printing beta equals alpha squared with single and double precision is shown on line 2 on the left-hand side and on the right-hand side. As you can see, there's some junk on the left-hand side, whereas the solution on the right-hand side is much more accurate. And the relative error between single and double precision in this case is shown on line 3. This might not be an issue for your code. However, this could be if you're dealing with systems with high condition numbers, which are very sensitive to these very small differences. There are additional compilation flags for debugging, such as the -G line flag, and that will cause a stack trace to be printed when a runtime error has occurred. Then there's the -M trace flag for memory allocation and deallocation, and this is useful for detecting memory leaks when using Fortran pointers. And there's the -NAN flag, which will initialize real and complex variables to signaling NAN, which will cause a runtime crash if these values are used before being initialized. I'll now talk about the additional tools that come with the compiler, such as the polishing feature. So to invoke the polishing feature using the NAG compiler is shown here. So NAG for equals polish, and there are quite a few options. You apply it to your code.f90, and your output is a new code. And the options can be one of the flags shown here. So -alter comments that will enable the polisher to change the comments, such as indenting. The array constructor brackets, you can change it to square or parenthesis slash. The square version is the more modern version. You can also use ID case to change the case sensitivity of variables or keywords. And X must be one of C, L, or U. C is for capitalized, where the first character is uppercase, everything else is in lowercase. L is everything is in lowercase, and U is everything is in uppercase. You can set the left margin, which is usually 0, the indentation blocks, which is usually 2. You can indent the comment marker, you can indent comments, and you can also have indent continuation by n spaces. You can also tell it to insert the kind keyword. So if you declare a variable real bracket real 64 : alpha, that becomes real kind equals real 64. You can also change the relational operators from the old Fortran 7.7 version, such as .eq, .le, to more modern versions, such as double equal, less than equal. And you can also insert double colons in variable declarations using -d : in DECLS. So integer I becomes integer : I. You can also change the character declarations. So that will change character *11 to character len equals 11. And so this is an example of polishing a code. So setting the left margin to 0, indentation to 2, keywords are in lowercase, identifiers such as variables are in lowercase, inserting double colons to the old code, old Fortran.f to new Fortran.f. So applying the previous command to the code on the left produces the code on the right. So as you can see, it's lowercase the keywords and the variable names. It's removed these horrible do loops and indented the block inside the do loop. It's inserted double colons in declarations and makes it much more readable. Then there's the enhanced polisher, which is another tool in the NAG Fortran compiler. It converts fixed form code into free form modern Fortran. To use this feature, the code cannot have compilation errors. You can also add keywords to actual arguments in procedure references. So to invoke the enhanced polisher, you call it with the -e polish flag. You apply it to your old code, and the -o is the output file, and that creates a modern code, such as source.f90. Applying the enhanced polisher to the left-hand code on the left-hand side produces the code on the right-hand side. The changes that have been made are that it has inserted modern comments using the exclamation, modern relational operators, it has inserted double colons in declarations, capitalized from uppercase. After applying the enhanced polisher, you can apply additional polishing features and the unifying precision feature. Now talk about real-world bugs caught by the NAG compiler. The first case study is the datetime library, which was declaring constants. This is shown on line 1. As you can see on that line, it's declaring a double precision variable 24, and the kind is real 64. However, the literal 24 is obviously an integer, and that's incorrect. And it doesn't have the E specifier. This was undetected by the Intel and GNU compilers. However, the NAG compiler caught this bug, and this was corrected to 24.0_real64 with a GitHub pull request. The next case study is a magnetohydrodynamics code, which was passing an actual argument that did not have the target attribute, whereas the corresponding dummy argument did have the target attribute. Within a procedure, a pointer was associated with the argument, which caused an internal compiler error when using the -C dangling flag. This bug was fixed in the NAG compiler, and subsequently it caught a runtime non-conformance in the code. And the non-conformance is taken from the Fortran standard. If the dummy argument has a target attribute and the effective argument does not have the target attribute, any pointers associated with the dummy argument becomes undefined when execution of the procedure completes, and the reference is given at the bottom. The next case study is the plot visualization library written in C, which has Fortran bindings or interfaces. plot was routinely built with the GNU compiler, and the Fortran bindings were extensively modernized using the NAG compiler. So the NAG compiler caught missing implicit none statements, had unused variables. It also enforced proper usage of the ISOC intrinsic module, proper use of real kinds. And this whole exercise took around 3 months. After that exercise, the plot's Fortran bindings portability significantly increased. I'll now talk about compiler characteristics. As I mentioned earlier, not all compilers are created equal. Some are better than others at certain things, and some are good at producing fast and optimized executables, and some are good at error detection and standards conformance. The NAG compiler firmly falls within the latter category, which will help you write correct and portable code, and portability is vital for the longevity of your code, particularly if you have a very large code. And that's because codes can outlive supercomputers and even compilers or even developers. So it's very important to have portable code. And the way you do that is by adhering to the Fortran standard as much as possible, and that provides the highest guarantee for portability, and the NAG compiler is really the stricter standards compliant compiler. So talked about different compilers having been very good at optimizing the code, and some are very good at error checking. So which compiler should I use? So this is a recommendation for a code development workflow. You start from the very left. You can use some static verification tools to do some basic error checking, and you can use the NAG compiler for strict standards and compliance checks and runtime checks. And that can be used in tandem with higher performant compilers such as Intel, IBM, or Cray. And that way you can create fast, correct, and portable code to create performance portable code. So the NAG compiler is really an indispensable tool for software development. and as it provides additional code modernization tools that I mentioned. So if you're interested in the NAG compiler, you can read about it from this URL. You can also download a trial version, and we can very easily create a trial key for you. And I'd like to end the presentation with a compiler challenge. I would really encourage you to try the compiler and try and compile your code with the NAG compiler without getting any warnings and errors. I run a Fortran workshop, and many people have been very surprised by the usefulness of the diagnostic messages created by the compiler. And now I'll end with question and answers. So the question received is the NAG compiler the only tool for verification? There are other static analysis tools such as FortCheck and CAMFOR. CAMFOR is free. FortCheck, I don't believe is free. The next question is, all these checks, what if the routine being called is in another file? Will it still detect constants or out of range accesses? What if you declare an array of size 5 and pass it into a subroutine in another file, which is declared to be size 10 and sets the first element 6? Will it detect that? You'll have to compile all your files with the NAG compiler to use these runtime error checks. And you have to compile your code with the same error checking flags as well to be able to use that feature. The next question is, how compatible are you with Intel Fortran? Demos?
There is no guarantee as far as I know, but I can't think of a counterexample of incompatibility. I think we have been able to mix it.
What about the character string lengths? The Intel compiler uses 64-bit integers for character string lengths. I'm not sure if the non-compiler does or not.
Yeah. I would not make any claims on that.
On Linux, you can't make any claims. On Windows, if you compile a program using the Intel compiler, if you make a DLL, then you can call that from the NAG Fortran compiler. You can't call static libraries though on Windows.
Okay, thanks. The next question is, FortCheck has been bought by another company. I don't think it can be bought anymore. So that's a comment about my previous answer. Another question coming in, when does NAG expect to achieve full Fortran 2018 standards compliance?
The standard's not been published yet. So.
Yeah, so the standard hasn't been published yet. The aim is to publish it obviously this year. I don't have any timelines. Usually it's a bit slow.
But remember, the NAG compiler has not even achieved Fortran 2008 or 15 compatibility, full compatibility yet. And neither have most of the compilers.
Yeah. So when the standard gets finalized, it's usually quite slow. Not all. Some compilers are quicker than others, so it's very difficult to get a timeline. Okay, just before I close, I just want to, we still have a bit more time left, so if anyone has any questions, I'll happily take them. There's another question sent by an attendee. I don't know the answer to that, but I will catch up with you via email, if that's okay with you. So if no one has any more questions, I'd like to thank everyone for the time and attention. Thanks very much, and goodbye.